There's a hidden music in the cosmos, a symphony played not by strings or wind, but by the remnants of dead stars, neutron stars. These incredibly dense objects, each one a city-sized cinder left behind after a supernova explosion, vibrate with frequencies so precise they could rival the finest-tuned instruments on Earth. Yet their song is nearly silent, carried not through air, but through the fabric of spacetime itself. What if I told you these cosmic giants hold secrets that could rewrite our understanding of the universe? Think of a neutron star as nature's most extreme tuning fork. Born from the violent collapse of a massive star, these objects pack more than the sun's mass into a sphere no wider than a metropolis. The gravitational forces at their surfaces are so intense that a single teaspoon of their material would weigh billions of tons. But here, where it gets even stranger, despite their unimaginable density, neutron stars aren't static. They quiver, they ring, they resonate with subtle vibrations that echo through space. These oscillations, known as, send ripples through their ultradense crusts, creating frequencies so precise that astronomers can use them like cosmic fingerprints to peer inside these enigmatic objects. What do these vibrations tell us? Everything from the star's internal structure to the bizarre state of matter lurking in its core. Some neutron stars pulse with such regularity they rival atomic clocks, while others shudder with violent quakes that release more energy than a million earthquakes. And then there are the ones that hum in harmony with unseen companions, their vibrations hinting at hidden partners like black holes or even stranger cosmic phenomena. This isn't just about studying distant stars. It's about decoding the universe's most extreme physics, where gravity bends space, matter crushes itself into exotic forms, and the very fabric of reality is pushed to its limits. So let's step into this silent symphony, where every vibration tells a story, and every neutron star holds a cosmic secret waiting to be heard. To grasp the sheer strangeness of a neutron star, picture taking the entire mass of our sun and squeezing it into a space smaller than Manhattan. The forces at work here defy everyday intuition. At their cores, protons and electrons are crushed together so violently that they merge into neutrons, creating a sea of matter so packed that even atoms can't retain their familiar structure. This isn't just dense material, it's matter pushed to a breaking point, where the rules of quantum physics and gravity lock in a cosmic tug-of-war. The birth of a neutron star is anything but quiet. It begins with the death throes of a massive star, one at least 8 times heavier than our sun. When such a star exhausts its nuclear fuel, its core collapses in a fraction of a second, triggering a supernova explosion so bright it can outshine an entire galaxy. What remains isn't just a corpse. It's a reborn object, spinning rapidly and crackling with magnetic fields trillions of times stronger than Earth's. Some neutron stars, called pulsars, beam radiation like cosmic lighthouses, sweeping the sky with clockwork precision. Others, known as magnetars, harbor magnetic fields so intense they could strip data from a credit card halfway across the solar system. But the real magic lies in their vibrations. Just as a bell rings when struck, neutron stars oscillate after disturbances, whether from crust fractures, magnetic upheavals, or even the gravitational pull of a nearby companion. These vibrations ripple through the star's interior, carrying clues about the mysterious matter inside. Some oscillations resonate at frequencies audible to humans if scaled up, while others pulse at rates detectable only by sensitive telescopes. Scientists compare these signals to seismic waves on Earth. By studying how they travel, we can map the star's hidden layers, just as geologists probe our planet's interior. What makes these cosmic tremors so valuable? They're pristine messengers from a realm where matter exists in states impossible to recreate on Earth. Deep within a neutron star, protons and neutrons may dissolve into a soup of quarks, or freeze into crystalline structures harder than diamond. Some theories even suggest pockets of strange matter, a hypothetical substance that could rewrite the laws of physics. Every quake, every hum, every flicker in a neutron star's rhythm brings us closer to answering one of astronomy's biggest questions. What happens to matter when gravity wins the moment a massive star exhales its last nuclear breath? The universe holds its own breath, just for a fraction of a second. Then, in a blaze of light visible across galaxies, the star's core implodes with unimaginable force. This isn't just an explosion, it's a cosmic metamorphosis. The outer layers blast outward in a supernova bright enough to outshine entire star clusters, while deep inside, the core crumples like paper in a fist. In less time than it takes to blink, gravity wins the battle against pressure, squeezing the star's heart into a sphere no bigger than a city. But this isn't just a shrinking act, it's a transformation so extreme it defies the very rules of matter. At these densities, atoms cease to exist. Protons and electrons, usually separate particles dancing around each other, are forced into a desperate merger. The star's core becomes a sea of neutrons so tightly packed that a single sugar cube's worth would outweigh Mount Everest. This is where the name Neutron Star comes from, but the reality is even wilder than the label suggests. The crushing gravity doesn't just rearrange particles, it warps the fabric of space-time around the newborn star, creating a gravitational field so intense it bends light itself. And then, like a cosmic top spun by the hand of a giant, the neutron star begins to whirl. The collapse turbocharges its rotation, sending it spinning hundreds of times per second, fast enough that if you stood on its surface, if you could survive the gravity, you'd experience a day in less than a millisecond. But the drama doesn't stop there. The star's magnetic field, already intense before the collapse, gets wound up like a spring during the implosion. The result: a magnetic force trillions of times stronger than Earth's, so powerful it could distort atoms from thousands of miles away. These extreme conditions, the dizzying spin, the crushing density, the magnetic fury, all conspire to make neutron stars cosmic tuning forks. Even the smallest disturbance, whether or the gravitational nudge of a passing asteroid, sends vibrations rippling through their ultradense interiors. These oscillations aren't just tremors, they're messengers carrying encoded information about the star's deepest secrets. Some vibrate like a drumhead, others twist like a wrung towel, each mode revealing a different layer of the star's hidden structure. And just like a bell's ring betrays cracks in its metal, the vibrations of a neutron star expose the mysteries of matter itself, where the ordinary becomes impossible and the impossible becomes routine. Among the most mesmerizing performers in the neutron star orchestra are the pulsars, celestial lighthouses that flash with metronomic precision. Picture a spinning top, but one so massive and energetic that it shoots twin beams of radiation from its poles like cosmic searchlights. As these beams sweep across space with each rotation, they create pulses so regular you could set your watch by them. Some spin hundreds of times per second, their rhythms so steady they rival the atomic clocks we rely on here on Earth. But these pulses aren't just a dazzling light show. They're the heartbeat of a neutron star, carrying encrypted messages about the chaos churning beneath their surfaces. The secret to their precision lies in the extreme physics governing these objects. A pulsar's rotation is stabilized by its mind-bending density, making it one of nature's most reliable timekeepers. Yet even these cosmic clocks aren't perfectly steady. Tiny hiccups in their pulses, called glitches, betray violent upheavals beneath the surface. Imagine a spinning ice skater suddenly tucking their arms in, speeding up imperceptibly. In a pulsar, these speed-ups can happen when the star's crust fractures or its superfluid core suddenly shifts, releasing energy like a wound-up spring. These microsecond stutters might seem insignificant, but to astronomers, they're seismic events, offering a fleeting glimpse into the star's hidden mechanics. What's even more astonishing is how pulsars reveal their vibrations through these pulses. Just as a guitarist can hear slight changes in a string's tension, scientists detect subtle shifts in a pulsar's rhythm caused by oscillations rippling through its interior. Some vibrations stretch the star like a rubber ball being squeezed, while others twist it like a wrung-out towel. Each mode resonates at a specific frequency, painting a sonic blueprint of the star's structure. By studying these vibrations, astronomers can map the layers of a neutron star as clearly as geologists map Earth's crust. Except here, the landscape is made of matter so dense it defies imagination. Pulsars don't just sing solo, they often perform in cosmic duets. When paired with another dense object like a black hole or white dwarf, their pulses become a gravitational stone. The way their rhythm subtly speeds up or slows down reveals the dance of spacetime itself, warped by their partner's mass. Some pulsars even hum in harmony with gravitational waves, their vibrations echoing the ripples predicted by over a century ago. It's as if the universe handed us a tuning fork to measure its most hidden forces, one precise pulse at a time. The magic of these cosmic lighthouses isn't just in their predictability, but in their imperfections. Every glitch, every wobble, every microscopic shift in timing is a clue waiting to be deciphered. They're not just dead stars, they're dynamic laboratories where matter, gravity, and magnetism collide in ways we're only beginning to understand. And with each pulse, they whisper the same tantalizing question. What else is hiding in the heart of a neutron star? These vibrations aren't random noise. They're precise cosmic harmonies, each with its own distinct signature. Like a bell struck by a hammer, a neutron star can resonate in multiple ways simultaneously. Some vibrations squeeze the star radially, making it pulse in and out like a breathing sphere. Others send ripples circling its equator like waves around a pond. There are even torsional oscillations, where sections of the crust twist against each other like a towel being wrung out in zero gravity. Each mode carries unique information about the star's hidden depths. Take the star's crust, for example, a crystalline layer just a kilometer thick but harder than any material known on Earth. When this ultradense shell fractures it triggers vibrations that ricochet through the star's interior. Scientists compare these quakes to earthquakes, but with one crucial difference. The energy released could power human civilization for centuries. These tremors excite various oscillation modes, much like how striking a piano key produces not just one note, but a blend of overtones. By analyzing these harmonic fingerprints, astronomers can determine whether the crust is smooth or fractured, rigid or elastic, details that reveal how matter behaves under pressures 1,000,000 times greater than Earth's core. The real lies in how these vibrations interact with the star's mysterious interior. Beneath the crust, neutron stars may contain oceans of superfluid neutrons, a bizarre state of matter that flows without friction. When vibrations pass through this quantum soup, they slow down or speed up in telltale ways, exposing properties invisible to telescopes. Some theories suggest deeper layers might harbor stranger substances, perhaps quark matter, where protons and neutrons dissolve into their fundamental particles. Each vibration acts like a sonar pulse mapping this alien landscape, showing where soft superfluid transitions into rigid crystalline matter. What makes these oscillations truly universal is their ability to warp spacetime itself. Predicted that massive accelerating objects should produce gravitational waves, ripples in the cosmic fabric. Neutron star vibrations do exactly that, broadcasting their rhythms across the cosmos not as sound or light, but as subtle distortions of space. Modern observatories like LIGO can now detect these whispers from billions of light years away. A single neutron star's hum might reveal whether its core contains exotic hyperon particles, or whether space-time behaves differently under extreme gravity. Some neutron stars perform duets with their environment. When one orbits a black hole or another dense object, tidal forces stretch and compress it rhythmically. These forced vibrations create resonance patterns distinct from, like the difference between a guitar string plucked versus one bowed continuously. Binary systems amplify these effects, sometimes producing gravitational waves at precise frequencies that could help measure cosmic distances with unprecedented accuracy. The beauty of this cosmic music lies in its imperfections. A perfectly smooth, symmetrical neutron star would vibrate in simple mathematical patterns. But real stars have mountains, tiny bumps just centimeters high yet massive enough to distort oscillation modes. Magnetic fields threading through the star add further complexity, acting like invisible fingers pressing on a drumhead. These flaws make each neutron star's vibrational signature unique, much like how a Stradivarius violin sounds distinct from a factory-made instrument. Listening to this silent symphony requires ingenious technology. Radio telescopes track subtle pulse timing variations in pulsars, while X-ray observatories measure surface temperature fluctuations caused by crust vibrations. Gravitational wave detectors capture the lowest notes, frequencies too deep for conventional astronomy. Together, these instruments form an interstellar orchestra pit, each adding its part to decode the neutron star's score. What we're hearing revolutionizes physics. Some vibrations suggest neutron star cores might be stiffer than predicted, challenging theories about quark matter. Others hint at superfluid vortices aligning like microscopic tornadoes beneath the crust. With every new observation, we're not just studying dead stars, we're stress testing the laws of physics under conditions no lab could ever recreate. The universe has handed us a tuning fork forged in supernovae, and its vibrations are rewriting textbooks one note at a time. The vibrations of a neutron star are far more complex than a simple hum. They're a layered chorus of motions, each revealing a different piece of the star's hidden anatomy. Take torsional oscillations, for example. Picture twisting a rubber ball between your hands, feeling the resistance as its surface strains against the motion. Now imagine that same twisting happening to an object with the mass of a sun, its crust, a crystalline layer denser than diamond, writhing under unimaginable gravitational forces. These twisting vibrations don't just deform the surface, they send shock waves through the star's magnetic field, creating ripples detectable across interstellar distances. Then there are the pressure-driven modes, which behave like sound waves trapped inside a colossal bell. In ordinary stars, sound travels through hot gas, but in a neutron star, it races through a quantum sea of neutrons so tightly packed they behave like a single, ultra-dense fluid. These vibrations can reach frequencies thousands of times higher than any audible sound, ringing out as the star's interior constantly adjusts to its own crushing gravity. Some modes even split into harmonics, like overtones on a guitar string, with each subtle variation exposing the density and composition of different layers deep within the star. Add another dimension to this cosmic symphony. Unlike earthquakes, which release energy along tectonic faults, neutron starquakes occur when the star's crust, under unbearable stress from spinning, cooling, or magnetic shifts, suddenly fractures. The energy released would dwarf every earthquake in human history combined, yet the vibrations themselves are precise, almost musical. Some quakes excite global oscillations, making the entire star resonate like a gong struck by a hammer. Others trigger localized vibrations, creating patterns akin to drumheads vibrating in specific spots. But not all oscillations come from within. Neutron stars locked in tight orbits with companions, whether white dwarfs, black holes, or other neutron stars, experience tidal forces that stretch and compress them rhythmically. These forced vibrations are like a cosmic version of holding a microphone too close to a speaker. The star's natural frequencies amplify, producing resonant tones that reveal its internal structure with extraordinary clarity. In systems where the neutron star pulls material from a companion, the infalling gas can strike the surface like raindrops on a drum, generating high-frequency oscillations that map the star's magnetic field geometry. Detecting these vibrations requires ingenuity, since neutron stars don't exactly send out audible sound waves. Astronomers rely on indirect signatures, subtle changes in the timing of a pulsar's radio pulses, flickers in X-ray emissions as the star's hot spots wobble, or even distortions in gravitational waves. Each method is like tuning a radio to a different station, catching glimpses of the same phenomenon through separate lenses. The result: a three-dimensional sonogram of a cosmic giant, where every tremor, every twist, every resonant note paints a clearer picture of the universe's most extreme matter. Detecting the silent symphony of neutron stars is like trying to eavesdrop on a conversation happening behind a soundproof wall. Except the wall is the vacuum of space, and the voices are vibrations too subtle for any ordinary microphone. Since these cosmic giants don't produce sound waves in the traditional sense, astronomers have become masters of cosmic detective work, piecing together clues from the faintest signals across the electromagnetic spectrum and beyond. One of the most precise tools in their arsenal is pulsar timing. Imagine a lighthouse beacon flashing with such regularity that even a microsecond deviation stands out like a missed heartbeat. Pulsars, those rapidly spinning neutron stars, emit beams of radiation that sweep past Earth like clockwork. But when the star's crust quakes or its interior shifts, these pulses arrive slightly early or late, changes so tiny they'd be lost in the noise of less precise cosmic phenomena. By tracking these minuscule timing glitches, scientists can reconstruct the star's vibrations as clearly as a seismograph records earthquakes. Some deviations reveal powerful enough to rearrange the star's entire magnetic field, while others hint at the slow creep of superfluid vortices swirling beneath the crust. Gravitational wave observatories like LIGO take this listening party to another dimension entirely. These instruments don't rely on light or radio waves. They sense the stretching and squeezing of spacetime itself. When a neutron star vibrates, its colossal mass warps the fabric of the universe around it, sending out ripples that travel billions of light years. The frequencies LIGO detects are often lower than any sound a human could hear, but when sped up, they reveal the star's oscillations like a cosmic fingerprint. Some events, like the famous collision of two neutron stars in 2017, produced gravitational waves that matched theoretical models of how these objects vibrate during catastrophic mergers, a validation that these stars truly do ring like bells when struck. Then there's the X-ray view. Neutron stars may be cold by stellar standards, but their surfaces still glow fiercely in X-rays, especially where magnetic fields funnel particles into searing hot spots. When the star vibrates, these hot spots wobble like a spinning top losing balance. Space telescopes like NASA's NICER instrument, mounted on the International Space Station, detect these subtle brightness fluctuations, mapping surface motions with precision down to millimeters, equivalent to spotting a pebble's ripple from orbit around Earth. Some oscillations appear as rhythmic flickers, revealing global vibrations that make the entire star expand and contract. Others show twisting patterns, evidence of torsional waves rippling through the crust like seismic S-waves on our planet. The real power comes when these methods combine. Pulsar timing catches the star's slow, grand oscillations, gravitational waves reveal its deepest resonant frequencies, and X-rays pinpoint surface disturbances. Together, they form a multi-messenger orchestra, each instrument tuned to a different part of the neutron star's vibrational spectrum. This synergy has already upended expectations. like discovering that some neutron stars have crusts 10 times stiffer than predicted, or that their cores might contain exotic phases of matter where neutrons dissolve into quark soup. What's next in this cosmic listening project? Future gravitational wave detectors like the space-based LISA mission will extend our hearing to lower frequencies, potentially catching the ultra-slow vibrations of supermassive neutron stars. Advanced X-ray telescopes could resolve surface quakes in real time, watching as magnetic upheavals trigger star-spanning seismic waves. And as pulsar timing arrays grow more sensitive, they might detect the background hum of countless neutron stars vibrating in unison. A galactic choir singing the hidden physics of matter pushed beyond breaking point. The silent symphony of neutron stars isn't just a curiosity, it's a revolution in how we study the universe. Every vibration, whether caught by radio waves, space-time ripples, or X-ray flickers, peels back another layer of these cosmic enigmas. And with each new observation, we're not just listening to dead stars, we're decoding the universe's most extreme physics, one oscillation at a time. Peering into a neutron star's interior is like trying to decipher a sealed cosmic letter, except the ink is made of vibrating space-time, and the paper is matter crushed beyond recognition. Those oscillations we've been exploring, they're not just tremors, they're precision tools, carving away the mystery layer by layer. Every vibration that ripples through the star's core behaves differently depending on what it encounters, slowing down in superfluid regions, speeding up through crystalline layers, or scattering entirely in zones where matter might exist as free quarks. It's the universe's most extreme game of Marco Polo, with physicists as the eager listeners. Take hyperons, for example, exotic particles that might form when neutrons, under unbearable pressure, start sprouting strange quarks like cosmic mutations. Normal matter can't sustain these particles, but inside a neutron star, they could dominate, turning the core into a zoo of unstable particles that flicker in and out of existence. Vibrations passing through such a region would distort in telltale ways, like light bending through a funhouse mirror. Some models even predict quark stars, objects so dense that neutrons surrender entirely, dissolving into a seething ocean of unbound quarks. If these exist, their oscillations would carry a unique acoustic signature, one we might already have glimpsed in the odd timing glitches of certain pulsars. The stakes go far beyond cataloging cosmic oddities. These vibrations test the very laws of quantum, the rules governing how quarks stick together. On Earth, we can't recreate neutron star conditions, not even in powerful particle colliders. But these stars are nature's ready-made laboratories, where matter is squeezed to limits that defy textbooks. When vibrations suggest a neutron star's core is softer than expected, it hints at free quarks sliding past each other like ball bearings. When they point to unexpected stiffness, it might mean quarks have frozen into crystalline patterns stranger than any sci-fi material. And then there's the space-time twist. Neutron stars don't just vibrate in 3 dimensions. Their oscillations warp the fabric of the universe around them, imprinting gravitational waves with clues about their interiors. It's as if the star is whispering its secrets not just through matter, but through the bending of reality itself. Recent gravitational wave detections from colliding neutron stars already show hints of resonance patterns that don't match pure neutron models, suggesting something exotic lurks inside. But the influence doesn't stop at the star's surface. These vibrations ripple outward, disturbing the star's magnetosphere, the zone where its monstrous magnetic field rules supreme. A single can trigger magnetic avalanches, rearranging entire field lines in seconds. This chaos births powerful X-ray bursts and gamma-ray flares, some so intense they've been detected across intergalactic distances. Even the star's surroundings aren't safe. Planets orbiting a pulsar, yes, they exist, would be bathed in periodic shockwaves, their atmospheres shredded by each stellar heartbeat. The most dramatic echoes occur in binary systems, where two neutron stars dance a hair's breadth apart. Their mutual vibrations, driven by tidal forces, create resonances that amplify like feedback in a microphone. Some models suggest these interactions could prematurely trigger or even set the stage for catastrophic mergers. It's a gravitational tango where every step sends tremors through spacetime itself, tremors we're now learning to decode. From the quantum oddities in their cores to the fireworks in their skies, neutron stars prove that a silent symphony can still shake the universe. Neutron stars may be solitary survivors of stellar explosions, but they're far from lonely giants. Their vibrations don't just echo inward, they ripple outward, reshaping their cosmic neighborhoods with invisible hands. Picture a pulsar with particle jets so powerful they carve cavities in surrounding gas clouds, like a cosmic blowtorch slicing through interstellar fog. These jets, channeled by the star's immense magnetic fields, don't just stream outward silently. They flicker and pulse in rhythm with the star's oscillations, turning entire nebulae into echo chambers for the neutron star's vibrations. Then there are the deadly dances of binary systems, where a neutron star and its companion engage in a gravitational tug-of-war. As the star's vibrations resonate through space, they create tidal forces that can shred nearby objects. Some neutron stars act like cosmic vampires, siphoning gas from their partners at nearly light speed. This stolen material doesn't just disappear. It spirals down magnetic field lines in screaming arcs, striking the neutron star's surface with enough energy to trigger X-ray bursts that outshine entire galaxies. The resulting shockwaves ripple back through the accretion disk, creating feedback loops of vibration that astronomers can detect as quasi-periodic oscillations, rhythmic flickers that betray the star's hidden tremors. But the real puppet master behind these interactions is the neutron star's magnetic field, a force so immense it defies earthly comparison. These fields don't just guide particles, they shape the star's very vibrations. Imagine taking every magnet on Earth, compressing their combined strength into an area the size of a sugar cube, then multiplying that by 1 trillion. That's the intensity we're dealing with. When a neutron star's crust shifts these magnetic fields don't just passively observe, they actively resist, like elastic bands stretched to their limits. This magnetic tension alters how vibrations propagate, suppressing some frequencies while amplifying others. The most extreme cases are magnetars, neutron stars with magnetic fields 1,000 times stronger than ordinary pulsars. Here, the field is so powerful it can literally twist the star's crust like taffy, generating vibrations through pure magnetic stress. These release energy equivalent to 1 billion atomic bombs, yet they're governed by the same physics as a guitar string vibrating under tension, just scaled up to cosmic proportions. The resulting oscillations create electromagnetic fireworks, bursts of gamma rays that can temporarily outshine the Milky Way, all choreographed by the interplay between crust and magnetic field. What makes these magnetic vibrations so revealing is how they bridge quantum physics and celestial mechanics. Deep inside the star, magnetic fields thread through the neutron superfluid like spaghetti through jello, creating vortices that can suddenly rearrange themselves. When these quantum tangles snap into new configurations, they send shockwaves rippling outward, first through the star's interior, then into its magnetosphere, and finally across light years of space as detectable electromagnetic pulses. It's a chain reaction that connects microscopic quantum phenomena to galaxy-spanning energy releases, all traceable through the neutron star's vibrational fingerprint. This magnetic symphony doesn't just play in one key. Some neutron stars exhibit mode switching, where their vibration patterns abruptly change as magnetic fields reconfigure beneath the surface. Others show gradual drift in oscillation frequencies as their fields slowly decay over. Each variation acts like a different instrument in the cosmic orchestra. A magnetar's screeching gamma ray glissando contrasting with a millisecond pulsar's steady magnetic hum. Together, they prove that to understand a neutron star's song, you must first listen to its magnetic heartbeat. The magnetic fields threading through neutron stars aren't just powerful. They're cosmic power lines crackling with enough energy to rewrite the rules of physics. Picture Earth's magnetic field, which gently guides compass needles. Now amplify that by a factor of a quadrillion, squeeze it into a sphere 20 kilometers wide, and set it spinning hundreds of times per second. What you get is a force so intense it can literally bend the star's solid crust, a crust 10 billion times stronger than steel, like putty in an invisible hand. These magnetic monsters don't just influence vibrations, they create them, twisting the star's surface until it snaps back in seismic waves that reverberate clear to the core. Magnetars take this magnetic mayhem to another level entirely. These rare neutron stars boast fields 1,000 times stronger than their already extreme cousins, so strong they can rip apart atoms from 50,000 kilometers away. When a magnetar's crust finally buckles under magnetic stress, the resulting doesn't just shake the star, it unleashes apocalyptic energy. In 2004, a magnetar halfway across the galaxy released a flare so powerful it temporarily ionized Earth's upper atmosphere from 50,000 light-years away. The vibrations from such events don't travel like ordinary seismic waves. They ride magnetic field lines like surfer, catching a tsunami, twisting spacetime itself as they propagate. What makes these magnetic vibrations so valuable to scientists is how they expose the star's hidden layers. Just as geologists use earthquake waves to map Earth's interior, astronomers track how magnetic oscillations travel through a neutron star. Some vibrations get trapped in the crust, bouncing between magnetic loops like echoes in a canyon. Others dive deeper, slowed by the frictionless quantum soup of superfluid neutrons swirling beneath. The most revealing are those that interact with the star's superconducting core, where protons pair up and flow without resistance, creating magnetic vortices that can suddenly rearrange themselves. When these microscopic shifts cascade upward, they trigger observable changes in the star's oscillation patterns, offering clues about conditions too extreme for any laboratory. The real magic happens when magnetic fields and vibrations team up to rewrite quantum physics. Under these extreme conditions, empty space itself becomes unstable, a phenomenon called vacuum polarization, where the magnetic field is so strong it distorts virtual particles popping in and out of existence. This quantum froth leaves fingerprints on the star's vibrations, subtly altering their frequencies in ways that could confirm or challenge our deepest theories of matter. Some models even suggest magnetars might host exotic particles predicted by string theory, their presence betrayed by telltale distortions in oscillation modes. These magnetic maestros don't keep their symphonies to themselves. Their vibrations ripple outward, shaking charged particles trapped in magnetic field lines. The result, cosmic lighthouses flashing not just with radio waves, but with coordinated X-ray pulses that dance to the star's resonant frequencies. Some magnetars emit quasi-periodic oscillations after giant flares, rhythmic X-ray flickers that match theoretical models of torsional vibrations in the crust. It's as if the star is broadcasting its seismic activity on an interstellar frequency, turning high-energy radiation into a carrier wave for its hidden dynamics. The most astonishing revelation might be how these magnetic vibrations bridge quantum weirdness and cosmic-scale phenomena. A single rearrangement of magnetic vortices in the core, a quantum event spanning, can trigger a releasing more energy than a solar flare. This microscopic to macroscopic connection makes neutron stars nature's ultimate particle accelerators, where the behavior of individual quarks influences stellar-scale oscillations. Every magnetic tremor carries encrypted messages about physics at scales we'll never replicate on Earth, written in frequencies only the universe's most sensitive instruments can decode. As we peel back these magnetic mysteries, we're not just studying dead stars, we're stress-testing the fundamental laws of reality under conditions where matter and magnetism blur into something stranger than fiction. The vibrations of these cosmic giants may soon answer questions that have puzzled physicists for decades. What happens to matter when magnetic fields overpower nuclear forces? Can space itself be torn apart by pure magnetism? The answers are ringing through the cosmos right now, carried on magnetic waves from the universe's most extreme tuning forks. The interior of a neutron star isn't just dense. It's a quantum playground where the ordinary rules of matter break down completely. At these unimaginable pressures, neutrons aren't just packed together like marbles in a jar. They dissolve into a bizarre quantum soup where particles lose their individuality entirely. Some regions may become superfluid, flowing with zero friction, while others could turn into superconductors, conducting electricity without resistance. These aren't just theoretical curiosities. They're states of matter so extreme they can't be recreated in any lab on Earth. Yet neutron stars don't keep these secrets entirely hidden. Their vibrations act like cosmic sonar, sending echoes through these exotic layers, each ripple encoding clues about what's happening deep inside. Superfluidity in neutron stars isn't like anything we see on our planet. Imagine a liquid that never slows down, never heats up, and climbs the walls of its container in defiance of gravity. Inside a neutron star's core, this isn't science fiction, it's reality. Neutrons, normally sluggish particles, pair up and move in perfect unison, creating a frictionless ocean beneath the crust. When vibrations pass through this superfluid, they don't dissipate like sound waves in air. They propagate with eerie efficiency, their frequencies subtly shifted by the quantum ballet beneath. Some oscillations even excite vortices, tiny whirlpools in the superfluid that rotate in perfect lockstep, like synchronized cosmic dancers. Then there's the possibility of superconductivity, where protons in the core pair up and conduct electric currents without losing energy. This isn't just about zero resistance, it's about magnetic fields getting trapped in microscopic whirls, creating a lattice of quantum flux tubes that vibrate like cosmic guitar strings. When shake the star, these magnetic vortices jostle and rearrange, altering the way oscillations travel. The resulting patterns could reveal whether the core is a uniform superconductor or riddled with islands of normal matter, a detail that would rewrite our understanding of quantum phase transitions under extreme conditions. The real prize lies in how these quantum effects might bridge theory of gravity with the strange world of quantum mechanics. Neutron stars are the only places in the universe where both theories collide at macroscopic scales. Their vibrations could carry signatures of quantum gravity, subtle distortions in spacetime that hint at a deeper theory, unifying these seemingly incompatible frameworks. Some models suggest that certain oscillation modes might leak energy into extra dimensions, a prediction stemming from string theory. Others propose that vibrations could reveal spacetime itself becoming granular at tiny scales, like a cosmic effect only visible under neutron star-level gravity. But studying these quantum whispers isn't easy. The signals are faint, buried in noise from cosmic radiation, interstellar gas, and the star's own turbulent magnetospheres. Detecting them requires telescopes sensitive enough to catch a pulsar's pulse arriving a femtosecond early, or gravitational wave observatories capable of sensing spacetime ripples smaller than an atomic nucleus. Even then, interpreting the data is like reconstructing a symphony from a single out-of-tune violin possible, but painstaking. The challenges don't stop there. Quantum behaviors in neutron stars don't follow tidy textbook models. Superfluids might exist alongside normal matter in patchwork layers, or superconductivity might abruptly vanish under certain pressures, creating phase boundaries that scatter vibrations unpredictably. Some theories even suggest that the core might contain strange matter, a form of quark goo stable enough to convert the entire star into an even denser object called a quark star. If true, such a transformation would send shockwaves through the star's oscillation patterns, leaving behind a telltale seismic fingerprint. What keeps scientists searching is the tantalizing possibility that these vibrations might answer questions that have puzzled physicists for a century. How does gravity emerge from the quantum world? What happens to spacetime at the smallest scales? The answers might be pulsing through the cosmos right now, encoded in the tremors of these dead stars, if only we can learn to listen closely enough. Detecting the faint vibrations of neutron stars is like trying to hear a whisper in a hurricane. The signals exist, but cosmic interference drowns them out at nearly every turn. Even the most sophisticated observatories face staggering challenges. Gravitational wave detectors like LIGO must sense distortions in spacetime smaller than 1/10,000th the width of a proton, while radio telescopes tracking pulsar glitches measure timing variations down to nanoseconds. The slightest terrestrial disturbance, a passing truck, ocean waves crashing miles away, can mask these delicate cosmic murmurs. And distance is no ally. A neutron star's oscillations lose energy as they cross light years, arriving at Earth as ghostly remnants of their original power. The interference doesn't stop with earthly noise. The universe itself is a chaotic symphony of competing signals. Gamma ray bursts, magnetar flares, and even the microwave hum left over from the Big Bang create a cacophony that obscures neutron star vibrations. Isolating the desired signal is akin to picking out a single violin in an orchestra playing at full volume. Some frequencies are completely absorbed by interstellar dust, while others get scrambled by magnetic fields threading through the galaxy. Even when we catch a clear signal, interpreting it requires untangling complex physics. A single oscillation mode might be altered by the star's spin, magnetic field, or even quantum effects in its core, all factors that demand supercomputer simulations to decode. Theoretical models themselves are riddled with unknowns. Scientists must account for exotic states of matter that have never been observed directly, like quark-gluon plasma or hyperon-dominated cores. A vibration that suggests a stiff crust in one model might imply a superfluid layer in another. Even basic properties, like the exact thickness of a neutron star's crust, introduce uncertainties that ripple through every calculation. It's like trying to reconstruct a shattered vase when half the pieces are missing, and the glue's properties are a mystery. Yet every successful detection is a watershed moment. The neutron star merger observed in 2017 didn't just validate gravitational wave astronomy. It revealed vibrations in the remnant object that matched predictions of neutron stars. Similarly, subtle timing glitches in pulsars like the Vela pulsar have exposed powerful enough to rearrange entire magnetic fields. These breakthroughs didn't come from a single instrument, but from networks of telescopes and detectors working in concert. Radio observatories catching pulse irregularities, X-ray satellites monitoring surface hotspots, and gravitational wave antennas feeling spacetime tremors. The future, however, promises tools that could turn whispers into shouts. Next-generation gravitational wave detectors like the telescope will boast sensitivities 10 times greater than current models, potentially catching neutron star vibrations from the far edges of the observable universe. Space-based interferometers like LISA will target lower frequencies, opening a new window into the slow, resonant hum of supermassive neutron stars. Meanwhile, quantum-enhanced sensors could reduce terrestrial noise to negligible levels, letting us hear cosmic vibrations without Earth's interference. Perhaps most exciting are the computational leaps on the horizon. Machine learning algorithms trained on simulated neutron stars are already spotting patterns human researchers miss, while 3D magnetohydrodynamic models now incorporate quantum effects once thought too complex to calculate. Combined with multi-messenger astronomy, correlating data from gravitational waves, neutrinos, and electromagnetic signals, these tools could soon paint the most detailed portrait yet of a neutron star's interior. The challenges are immense, but so are the stakes. Every vibration we detect carries encoded secrets about matter, gravity, and the universe itself. With each technological leap, we're not just building better instruments, we're fine-tuning our ability to listen to the cosmos' most enigmatic performers. The next generation of telescopes and detectors won't just listen to neutron stars, they'll conduct their symphony with unprecedented precision. The telescope, a future gravitational wave observatory buried deep underground to shield it from Earth's vibrations, could detect neutron star oscillations from the earliest epochs of the universe. Unlike current detectors that catch only the loudest crashes of merging stars, this instrument will sense the subtlest quivers, the equivalent of hearing a pin drop across a concert hall. Its triangular design, with laser arms stretching 10 kilometers through vacuum tunnels, will pinpoint vibrations 3 times fainter than LIGO can today, revealing neutron star dynamics we've only theorized about. Meanwhile, the space-based LISA mission will open an entirely new frequency range. Imagine trying to understand an orchestra by hearing only the piccolos. That's our current gravitational wave view of neutron stars. LISA's trio of satellites, trailing Earth in solar orbit, will catch ultra-low frequency vibrations too deep for ground detectors. These could include the slow, resonant hum of supermassive neutron stars or the tidal vibrations of binary systems years before they collide. It's like adding subwoofers to our cosmic headphones, finally hearing the bass notes of the neutron star symphony. X-ray astronomy isn't standing still either. Upcoming missions like ESA's Athena and NASA's Lynx will carry mirrors so precise they could resolve a dime on the moon's surface. Pointed at neutron stars, these telescopes will track surface hotspots wobbling by mere millimeters, directly mapping crust oscillations in real time. Some designs even incorporate X-ray polarimeters to measure how vibrations twist the star's magnetic field, like watching a cosmic lava lamp reveal internal currents. The real game changers might be quantum sensors now in development. Atomic interferometers, which use the wave nature of atoms to measure infinitesimal forces, could one day detect neutron star vibrations without relying on electromagnetic signals at all. Picture a device sensitive enough to feel space-time ripples from a star's oscillation as they pass through Earth, a gravitational stethoscope pressed against the universe's chest. These tools won't just collect better data, they'll discover entirely new classes of vibrations. Current models predict oscillation modes that should exist but remain hidden, like waves that ripple through exotic core matter or crustal shear waves trapped between magnetic field lines. There might even be dark matter quakes vibrations triggered when hypothetical particles accumulate inside the star. Every new frequency discovered will be another note in our cosmic sheet music, helping us reconstruct the neutron star's full composition. What does this mean for cosmic competitors? While black holes dominate gravity wave detections with their violent mergers, neutron stars offer something unique, a sustained vibrational fingerprint that persists between cataclysms. White dwarfs, though plentiful, lack the density to produce such rich oscillations. Magnetars come close with their magnetic symphonies, but their vibrations are often drowned in gamma-ray static. Neutron stars strike the perfect balance, dense enough to warp spacetime with their tremors, yet structured enough to ring with complex harmonics. The coming decade will blur the line between astronomy and quantum physics. As we decode these vibrations, we're not just studying stars, we're stress-testing matter itself under conditions no lab can replicate. Will the core prove to be quark matter or hyperons? Does spacetime become granular near the surface? The answers are vibrating in the darkness, waiting for instruments sensitive enough to hear them. Black holes may be the universe's ultimate cosmic vacuum cleaners, sucking in everything that crosses their event horizons. But neutron stars are the universe's most extreme physics laboratories, places where matter doesn't disappear but gets compressed into forms so bizarre they challenge our understanding of reality. While black holes swallow light and information whole, neutron stars wear their secrets just beneath the surface, vibrating with clues we can actually detect. Both objects warp spacetime so severely that time slows to a crawl near them, and both generate gravitational waves when they collide. Yet here's the crucial difference. When neutron stars vibrate, they broadcast their internal structure across the cosmos, while black holes remain silent enigmas, their interiors forever hidden behind an event horizon. This distinction makes neutron stars invaluable to scientists. Imagine trying to study a musical instrument that's been locked inside a soundproof box. That's the challenge of probing a black hole. Now picture that same instrument placed on a stage, resonating with every note. That's a neutron star. Its vibrations allow us to test theories about matter at densities so high they approach the threshold of black hole formation. Some neutron stars teeter right on that edge, their cores possibly harboring quark matter or other exotic states that might represent the final form of matter before complete gravitational collapse. By studying their oscillations, we're essentially poking at the boundary between what we can observe and what disappears forever into a singularity. The connection between these cosmic heavyweights goes even deeper. When two neutron stars collide, they don't always form another neutron star. Sometimes they birth a black hole. The transition point between these outcomes remains one of astrophysics' great mysteries, and vibrations hold the key. Certain oscillation patterns could reveal whether a neutron star is about to cross that threshold, its core becoming so dense that not even neutron degeneracy pressure can resist gravity's pull. This isn't just academic. Such events produce the gold and platinum in our jewelry and the uranium in our nuclear reactors, scattering heavy elements across the cosmos in spectacular explosions. Yet for all their differences, neutron stars and black holes share an unexpected kinship in how they influence their surroundings. Both create extreme environments where matter behaves in ways impossible to replicate on Earth. Around a black hole, we see accretion disks glowing with X-rays as gas spirals toward oblivion. Around a neutron star, similar disks form, but here the material eventually crashes onto a solid surface, triggering nuclear explosions visible across intergalactic distances. Both objects can power jets of particles moving at nearly light speed, though neutron stars add their own twist. These jets often pulse in sync with the star's rotation, creating the lighthouse effect we observe as pulsars. The gravitational waves they produce tell complementary stories too. Black hole mergers create clean, simple wave patterns, the signature of pure spacetime curvature. But when neutron stars collide, their vibrations continue ringing through the gravitational wave signal long after impact, carrying information about the resulting object's composition. Some mergers produce short gamma-ray bursts followed by prolonged afterglows, the astrophysical equivalent of a cosmic fireworks finale. Others leave behind a rapidly spinning, supermassive neutron star that may endure for minutes or before collapsing into a black hole, its vibrations gradually fading as the event horizon forms. This interplay between observation and mystery makes neutron stars ideal bridges in our cosmic understanding. They let us study physics at conditions approaching a black hole's edge while still leaving room for discovery. Their vibrations provide something black holes never can, a way to test our theories against observable reality. And as we'll see next, these same oscillations might hold clues to one of humanity's oldest questions. Could the universe be humming with life? And might neutron stars help us find it? Neutron stars may seem like the last places we'd search for life. Their surface is scorched by radiation, their gravity strong enough to shred molecules, and their magnetic fields capable of sterilizing entire solar systems. Yet these cosmic extremes might hold unexpected connections to life's potential in the universe. Take pulsar planets, for example, worlds orbiting the corpses of dead stars. One of the first exoplanets ever discovered wasn't found around a sun-like star, but circling a pulsar called Pulsar B1257+12. Bathed in lethal X-rays and gravitational tides, these planets shouldn't exist, let alone sustain life. But nature thrives in paradox. Just as Earth's extremophiles survive volcanic vents or Antarctic ice, life might find a way in the pockets of a pulsar system, perhaps deep underground where a thick crust shields against radiation, or in tidally heated oceans kept liquid by gravitational squeezing. The influence of neutron stars extends far beyond their immediate vicinity. When two of these dense objects collide, they send gravitational waves rippling through space-time, cosmic tremors that subtly jostle every atom in their path. While imperceptible to us, these waves could theoretically trigger seismic activity on distant worlds, stirring subsurface oceans or volcanic systems. It's an interstellar butterfly effect. A merger occurring light years away might contribute to maintaining geothermal heat on an otherwise frozen exoplanet, creating temporary oases for life in the cold depths of space. Some researchers even speculate that ancient neutron star collisions could have seeded galaxies with heavy elements essential for life: gold, platinum, uranium, scattering stardust that would later form rocky planets like Earth. Among the most studied neutron stars is the Crab Pulsar, the spinning heart of a supernova witnessed by Chinese astronomers in 1054. Rotating 30 times per second, this celestial dynamo powers one of the most intricate nebulae we've observed, a glowing web of gas and magnetic fields where high-energy particles dance to the pulsar's rhythm. Then there's PSR J0348+0432, a pulsar so dense it approaches the theoretical limit before collapsing into a black hole. Its rapid spin and intense gravity make it a natural laboratory for testing general relativity under extreme conditions. But perhaps no neutron star captivates like PSR B1937+21, the original millisecond pulsar. Spinning an astonishing 642 times per second, its surface moves at nearly a quarter the speed of light. The forces at play here are so extreme that if you could stand on its surface and survive the crushing gravity, you'd witness time dilation so severe that a minute for you would be years for distant observers. These remarkable objects aren't just cosmic curiosities. They're keys to understanding how the universe operates at its most fundamental levels, and how even the harshest environments might play unexpected roles in life's grand story. Among neutron stars, few shine as brightly in human history as the Crab Pulsar. Born from a supernova explosion so brilliant it was recorded by Chinese astronomers in 1054 AD, this spinning remnant continues to dazzle modern scientists. Nestled at the heart of the Crab Nebula, its 30 times per second rotation powers an entire cosmic light show, jets of particles screaming outward at nearly light speed, illuminating gas clouds like a celestial disco ball. But beyond the spectacle lies something even more fascinating: the crab's vibrations. Precise timing of its pulses reveals tiny glitches, sudden speed-ups where the star's crust momentarily unlocks from its superfluid interior, releasing pent-up energy like a wound spring snapping. Each event leaves behind a seismic fingerprint, helping physicists map the star's hidden layers with astonishing precision. Then there's Magnetaris GR 1806-20, a neutron star so magnetically ferocious it makes ordinary pulsars seem tame. In 2004, this cosmic powerhouse unleashed a gamma-ray flare so intense it temporarily altered Earth's ionosphere from 50,000 light-years away. What makes magnetars truly unique are their vibrations, driven not just by crustal quakes, but by magnetic field lines snapping like over-tightened guitar strings. These events produce quasi-periodic oscillations, X-ray flickers that match theoretical models of how magnetized neutron stars vibrate when their surfaces rupture under magnetic stress. It's as if the star is screaming in frequencies only our most sensitive telescopes can hear, each note betraying the unimaginable forces at play beneath its surface. No discussion of neutron star celebrities would be complete without the Taylor binary, a pair of neutron stars whose decaying orbit delivered the first concrete proof of gravitational waves long before LIGO's direct detection. Discovered in 1974, this cosmic dance partners gradual matched predictions with breathtaking accuracy, their orbital energy bleeding away as spacetime ripples. But here's the twist: their mutual vibrations go beyond gravity waves. As they spiral closer, tidal forces distort each star's shape, creating resonant oscillations that subtly alter their pulsar signals. These tidal vibrations offer a rare glimpse into neutron star structure, revealing how rigid or fluid they behave when stretched by a companion's gravity. The true magic happens when science meets art to translate these cosmic vibrations into experiences we can see and hear. Collaborations between astrophysicists and sound designers have transformed neutron star oscillations into audible frequencies, letting us hear a magnetar's quake as a descending tone or a pulsar spin as a rhythmic beat. Visual artists take it further, rendering vibrations as rippling surface maps or magnetic field animations that make the invisible tangible. These creations aren't just beautiful, they're research tools. Data helps scientists spot patterns in glitch events, while 3D visualizations reveal how oscillation modes propagate through stars. It's a reminder that understanding the universe requires both precise measurement and creative imagination, two lenses focusing on the same extraordinary truth. These stellar celebrities prove neutron stars are more than cosmic oddities. They're dynamic characters in an ongoing astrophysical drama. The crab shows us how stellar corpses can power nebulae form. Magnetars demonstrate how magnetic fields can rival gravity in shaping a star's behavior. The Taylor binary taught us spacetime itself can vibrate. Together, they form a cosmic ensemble where each performer's unique rhythms reveal different verses of the same universal song, one we're only beginning to understand. Art and science collide in the most extraordinary ways when it comes to neutron stars. These cosmic vibrations, imperceptible to human senses, become breathtaking experiences through collaborations between astrophysicists and multimedia artists. Take gravitational wave data, normally represented as squiggly lines on a graph, and feed it through audio software, and suddenly you're listening to the universe's deepest rhythms. The chirp of colliding neutron stars, the resonant hum of a magnetar's quake, even the eerie whistles of a pulsar spin, all translated into frequencies our ears can process. It's not just creative license. These help researchers identify patterns that might slip past the eye, turning abstract data into something visceral and immediate. Visual artists take this a step further, transforming oscillations into shimmering dynamic models. Picture a neutron star's surface rendered as a rippling sphere, its crust warping under magnetic stress like liquid metal. Some visualizations use color gradients to represent density changes, deep blues where matter compresses, fiery reds where it fractures, while others animate gravitational waves as concentric rings pulsing through spacetime. These aren't mere illustrations, they're research tools. A 3D model of torsional vibrations might reveal how it propagates, showing why certain frequencies dampen faster than others. When a magnetar's magnetic field lines snap and recoil, visualizations make the invisible violence tangible, tracing energy pathways that theoretical equations alone could never convey so intuitively. The magic lies in how these creative interpretations democratize cosmic discovery. A scientist might spend years analyzing neutron star seismology, but a single or animation can communicate its essence in seconds. Museums and planetariums now showcase these works, letting visitors hear a pulsar's heartbeat or see space-time bend under a neutron star's weight. Even educational apps use interactive models where users tweak parameters, adjust a star's density or magnetic field strength, and watch how its vibrational modes shift in real time. Suddenly, astrophysics isn't locked behind equations, it's something you can feel. This synergy between disciplines has roots in centuries of scientific storytelling. Galileo sketched the moon's craters to share his telescopic discoveries. Images turned nebulae into public wonders. Today's artists wield algorithms and immersive tech, but the goal remains the same: to bridge the gap between data and wonder. When a musician scores a neutron star's vibrations as a haunting cello piece, or a VR designer lets you stand on a pulsar's surface as it quakes, they're not simplifying the science. They're revealing its emotional core, reminding us that the universe isn't just numbers, it's a grand, dynamic performance we're only beginning to witness. The evolution of neutron star research mirrors this artistic journey. Early radio telescopes could barely detect pulsar pulses. Now we track vibrations across gravitational waves, X-rays, and quantum sensors. Each leap in technology, like LIGO's first detection of merging neutron stars in 2017, unlocks new creative possibilities. Those collisions didn't just confirm predictions. They inspired symphonies, gallery installations, and even dance performances choreographed to the star's fatal spirals. As our tools grow sharper, so does our capacity to experience the cosmos not just as observers, but as participants in its silent symphony. The story of neutron star research reads like a cosmic detective novel, with each breakthrough peeling back another layer of these stellar enigmas. It all began unexpectedly in 1967, when doctoral student Bell noticed an unusual bit of scruff in her radio telescope data. A repeating pulse so precise it initially sparked speculation about extraterrestrial signals. These rhythmic blips, later named pulsars, became the first concrete evidence of neutron stars' existence, though the idea had been theorized decades earlier. Bell's discovery cracked open an entirely new field of astronomy, proving that the universe contained objects denser than anything previously imagined, spinning faster than kitchen blenders while beaming radiation like cosmic lighthouses. The 70s and 80s saw pulsars evolve from curiosities into scientific powerhouses. The detection of the first binary pulsar, PSR B1913+16, by and Joseph Taylor in 1974, transformed these objects into precision tools for testing general relativity. As the two neutron stars spiraled closer, their orbital decay matched predictions of energy loss through gravitational waves with stunning accuracy. A discovery that earned the researchers the 1993 Nobel Prize and hinted at phenomena we wouldn't directly observe for another 4 decades. Meanwhile, X-ray telescopes revealed even stranger neutron star varieties, like accretion-powered pulsars siphoning material from companion stars and magnetars, with magnetic fields strong enough to distort atoms from thousands of kilometers away. The 21st century ushered in the era of multi-messenger astronomy, where neutron stars became cosmic stones. The crowning achievement came in 2017, when gravitational wave detectors LIGO and Virgo felt the spacetime ripples of two neutron stars colliding, an event simultaneously witnessed by telescopes across the electromagnetic spectrum. This single observation confirmed neutron star mergers as factories for heavy elements like gold and platinum, revealed the origins of short gamma-ray bursts, and provided the most stringent test yet of gravity's speed. The data even hinted at the mysterious state of the post-collision remnant, with gravitational wave frequencies suggesting a neutron star that may have briefly resisted collapsing into a black hole. Each milestone has been a stepping stone to greater mysteries. The discovery of pulsar planets in the 90s challenged assumptions about where worlds could form. Precise pulsar timing arrays in the 2000s unveiled gravitational wave backgrounds from countless cosmic collisions. And recent observations of neutron star vibrations, whether through X-ray flickers, radio timing glitches, or gravitational wave harmonics, continue to push the boundaries of quantum physics and materials science. These aren't just academic triumphs, they're chapters in humanity's quest to understand matter's ultimate limits, written in the vibrations of stars that refuse to stay silent. Beyond laboratories and telescopes, neutron stars have sparked imaginations across cultures. They've inspired everything from futuristic energy sources in sci-fi, remember the pulsar-powered warp drives in Star Trek, to metaphors in music and poetry. The very concept of a city-sized object heavier than our sun bends the mind, making neutron stars perfect canvases for storytelling. Even their discovery story carries cultural weight. Bell overlooked contributions highlighting systemic biases in science, while the global collaboration behind gravitational wave astronomy showcases how shared curiosity can transcend borders. Whether as scientific marvels or cultural symbols, these cosmic giants remind us that the universe's most extraordinary phenomena often hide in plain sight, waiting for the right moment and the right tools to reveal their secrets. Neutron stars have leaped from astrophysics journals to the silver screen, becoming cosmic celebrities in their own right. Science fiction authors were among the first to recognize their storytelling potential. Arthur C. A fall of imagined spacecraft using pulsar navigation decades before scientists considered it possible. The film Interstellar brought neutron star physics to multiplexes, with its portrayal of gargantua's tidal forces borrowing directly from real pulsar research. Even video games have embraced their educational power, players piloting through Elite Dangerous must carefully navigate the relativistic jets of in-game neutron stars, learning through gameplay how these cosmic powerhouses can both destroy ships and supercharge their engines. What makes these stellar remnants such compelling backdrops for stories? Their very existence challenges human perception of reality. A teaspoon of neutron star material weighing billions of tons, surface gravity so strong it bends light like a funhouse mirror. These aren't just plot devices, they're natural thought experiments that push imagination to its limits. The novel Dragon's Egg by Robert Forward took this literally, envisioning life evolving on a neutron star's surface where chemical reactions occur at femtosecond speeds. While biologically improbable, such stories serve a deeper purpose. They make the inconceivable tangible, helping audiences grasp cosmic extremes through narrative. The cultural impact goes beyond fiction. Neutron stars feature in symphonic works like Pulsar by composer John, their rhythms translated into percussion sequences. Museum exhibits worldwide use interactive pulsar models to demonstrate spacetime curvature, while planetarium shows project gravitational wave visualizations set to original scores. This artistic cross-pollination does more than entertain. It builds bridges between abstract science and public understanding. When Marvel's Doctor name-dropped a Magnetar in Avengers Endgame, it sparked enough online searches to crash astrophysics education websites. Yet with great fascination comes ethical responsibility. The same vibrations that reveal neutron star secrets could theoretically be harnessed for destructive applications if weaponized technologies ever advance to cosmic scales. More pressing are the questions surrounding resource exploitation. Some proposals suggest mining neutron star mergers for rare heavy elements, raising concerns about interplanetary conservation. There's also the philosophical dimension. Should we alter these cosmic laboratories through future stellar engineering, or preserve them as natural testaments to universal forces? These dilemmas mirror earlier debates about lunar protection or asteroid mining, but with higher stakes. Neutron stars aren't just celestial objects, they're archives of physical law written in extreme conditions. Their vibrations encode information about fundamental forces that shape the universe, making them irreplaceable scientific treasures. As detection methods improve, we're effectively developing cosmic surveillance capabilities, able to monitor stellar interiors across galactic distances. This power carries an implicit duty to study responsibly, ensuring our growing understanding of neutron stars benefits all humanity rather than becoming yet another frontier for conflict. The cultural journey of neutron stars, from theoretical oddities to storytelling staples to ethical flashpoints, reflects humanity's evolving relationship with the cosmos. Each pulsar featured in a film, each magnetar described in a novel, serves as both entertainment and education, subtly preparing society for the day when these objects transition from distant curiosities to active considerations in our interstellar future. The vibrations we detect today may one day resonate through policy decisions about our place in the universe. Ethical questions in astrophysics often lurk beneath the dazzling discoveries, like shadows cast by neutron stars themselves. Consider the dilemma of resource allocation. Building a single next-generation telescope can cost billions, funds that could alternatively address climate change or global health crises. Yet these instruments do more than satisfy curiosity. The same technology developed to detect gravitational waves from colliding neutron stars now enhances earthquake early warning systems. Algorithms created to analyze pulsar signals improve medical imaging. The line between pure and applied science blurs when knowledge spills across disciplines in unexpected ways. International collaboration presents another ethical tightrope. Cutting-edge observatories like the Square Kilometre Array span continents, requiring cooperation between nations with competing political agendas. Data from gravitational wave detectors flows freely across borders, but access to observation time on premier telescopes remains uneven. Smaller nations and underrepresented researchers often find themselves sidelined in the race for cosmic discoveries. This imbalance isn't just unfair. It risks leaving entire regions unprepared for the coming era of multi-messenger astronomy, where understanding neutron star collisions could mean the difference between spotting an Earth-threatening gamma ray burst or missing it entirely. The environmental impact of astrophysics lingers as another pressing concern. Radio telescopes consume enough electricity to power small towns, while rocket launches for space-based observatories leave carbon footprints. Some institutions now offset these impacts with solar-powered facilities and greener cooling systems, but the field faces growing pressure to align with planetary sustainability goals. Even light pollution from observatories conflicts with indigenous stargazing traditions, prompting delicate negotiations about land use. These tensions remind us that studying the cosmos shouldn't come at the cost of harming our own world. Surprisingly, amateur astronomers are becoming vital allies in addressing these ethical challenges. Citizen science projects like At Home harness idle computing power from volunteers worldwide to analyze pulsar data, democratizing access to discovery. Backyard observers with modest telescopes now contribute to monitoring magnetar outbursts through organizations like the American Association of Variable Star Observers. This distributed approach not only expands scientific capacity, but fosters global engagement. A farmer in Kenya and a student in Norway can collaborate on classifying neutron star phenomena through platforms like. Their participation helps balance the scales, proving you don't need a PhD or billion-dollar equipment to advance our understanding of these cosmic giants. The most profound ethical lesson neutron stars offer might be their silent testimony to cosmic impermanence. These stellar remnants outlast civilizations, cultures, and even planets, yet their very existence reminds us of nature's fragility. A massive star must die violently to create one. As we debate how to study them responsibly, their vibrations carry an unspoken message. Knowledge pursued with wisdom and shared with equity becomes the true legacy of any civilization. Citizen scientists have become the unsung heroes of neutron star research, turning home computers into cosmic observatories. Imagine a teacher in Brazil, a retiree in Japan, and a student in Norway all contributing to cutting-edge astrophysics while sipping morning coffee. Through initiatives like At Home, over 500,000 volunteers donate idle computing power to sift through gravitational wave data, their machines forming a planetary-scale supercomputer. This distributed network has already discovered dozens of previously hidden pulsars, including some in binary systems that test theories with unprecedented precision. Other projects, like the based Pulsar Hunters, train amateur astronomers to spot anomalies in radio telescope data, anomalies professional researchers might overlook amid the noise. The collective power of these volunteers creates something remarkable, a living, breathing scientific process where curiosity transcends borders and expertise. What makes these contributions so invaluable isn't just the extra processing power, it's the fresh perspectives. In 2019, a German high school teacher participating in At Home helped identify a rare black widow pulsar, a system where the neutron star slowly evaporates its companion star. Professional astronomers had scanned the same data, but missed the subtle timing variations the teacher's keen eye caught. Stories like this underscore a profound truth. The universe speaks in whispers, and sometimes it takes a chorus of listeners to hear them clearly. Even backyard telescope owners contribute by monitoring known pulsars for sudden glitches or flares, creating a grassroots early warning system for magnetar eruptions. Yet for all we've learned, neutron stars guard their deepest secrets fiercely. One enduring mystery is the true nature of their cores. Vibrational data suggests some neutron stars might contain quark matter, a state where protons and neutrons dissolve into their fundamental particles. But is this quark soup uniform, or does it form crystalline patterns? Another puzzle involves fast radio bursts, brief, intense cosmic signals some theories link to magnetar quakes. Why do some neutron stars produce these energetic flares while others remain quiet? Then there's the riddle of pulsar anti-glitches, where stars mysteriously slow down instead of speeding up during crustal shifts. Each anomaly forces us to reconsider what we know about matter under extreme conditions. Perhaps the most tantalizing question involves the upper size limit of neutron stars. At what point does gravity overwhelm neutron degeneracy pressure, collapsing the star into a black hole? Recent observations of gravitational waves from merging neutron stars hint that this threshold might be lower than predicted, suggesting unknown physics at play. Some vibrations detected post-merger align poorly with current models, implying cores might contain exotic particles like hyperons or even free-floating quarks. These aren't just academic musings. Answers could rewrite our understanding of nuclear physics, influencing everything from energy production to materials science. The collaboration between professionals and citizen scientists has never been more crucial. As new telescopes like the Square Kilometre Array come online, they'll generate more data in a day than past decades combined, an avalanche of information needing human intuition to interpret. Projects are already training AI to assist, but the human element remains irreplaceable. Whether it's a retiree spotting a pulsar's irregular heartbeat or a classroom analyzing archival X-ray data, these collective efforts prove that unraveling the universe's grandest mysteries isn't just for elite institutions. The silent symphony of neutron stars plays for everyone, and sometimes the most important notes are heard by those who listen simply for the joy of discovery. Unsolved mysteries swirl around neutron stars like cosmic fog, concealing answers that could rewrite physics itself. Take their cores, what lurks in those unimaginably dense depths. Current models suggest neutrons might dissolve into a sea of free quarks, but some vibrations hint at something stranger. Could there be stable, strange matter, a hypothetical form where quarks reorganize into configurations impossible under normal conditions? Then there's the puzzle of magnetar flares, violent outbursts releasing more energy in milliseconds than our sun emits in centuries. These aren't just scaled-up solar flares. They're magnetic reconnection events so powerful they twist spacetime itself. Yet we still don't fully understand why some magnetars erupt while others stay quiet. The intrigue deepens with theoretical quark stars, objects so dense they make neutron stars seem almost fluffy. Predicted but never confirmed, these would form when neutrons surrender entirely, collapsing into pure quark matter. A handful of pulsars with unusually high densities and peculiar vibration patterns might already be quark stars in disguise, their oscillations carrying telltale signatures of this exotic state. Proving their existence would mean discovering an entirely new class of celestial object, one that defies conventional astrophysics. Yet neutron stars don't keep their secrets to themselves. Their mysteries ripple across scientific disciplines. Gravitational wave researchers chase the faint echoes of colliding neutron stars to probe quantum gravity. Nuclear physicists study their vibrations like cosmic lab reports, testing how matter behaves under pressures a billion times stronger than anything replicable on Earth. Even materials scientists pay attention. The crust of a neutron star, with its crystalline structure harder than diamond, inspires theories about ultra-strong materials. Perhaps most surprisingly, these stellar remnants are quietly reshaping artificial intelligence. Machine learning algorithms trained on pulsar data now help detect gravitational waves and cancer tumors alike, proving that decoding the universe's extremes can yield tools for earthly challenges. Meanwhile, quantum physicists pore over magnetar observations, wondering if their monstrous magnetic fields could reveal clues about harnessing nuclear fusion. The greatest lesson neutron stars teach isn't just about stars, it's about curiosity itself. Every unanswered question, from quark matter to magnetic fury, reminds us that the universe reserves its most profound truths for those who listen closely to its silent symphony. And as we'll see next, the instruments we're building to hear that symphony are opening doors we never knew existed. Neutron stars serve as cosmic bridges, linking astrophysics to disciplines far beyond their stellar origins. In nuclear physics labs worldwide, scientists recreate fractions of a neutron star's crushing pressure using diamond anvil cells, devices that squeeze materials between gem-quality diamonds to simulate conditions a million times Earth's atmosphere. These experiments reveal how matter behaves when protons and neutrons surrender to gravity's grip, offering clues about the exotic states that might exist in a neutron star's core. Meanwhile, particle accelerators like the Large Hadron Collider smash heavy ions at near-light speeds, briefly forming quark-gluon plasma, a primordial soup that may mirror the universe's first microseconds or the depths of a collapsing stellar core. Each collision is a miniature supernova, a fleeting window into physics we can't otherwise observe. The computational challenge of modeling neutron stars pushes supercomputers to their limits. Simulating just 1 millisecond of a magnetar's magnetic field evolution requires petabytes of data, tracking how trillion Gauss fields twist the star's crust like taffy. These simulations borrow techniques from weather forecasting and fluid dynamics, adapted to environments where quantum effects dominate and gravity warps spacetime itself. Machine learning now accelerates this process. Neural networks trained on known pulsar data can predict glitch behavior or identify gravitational wave signatures in noisy datasets, transforming how we interpret cosmic vibrations. This interdisciplinary cross-pollination yields unexpected breakthroughs. Quantum physicists study neutron star oscillations to test theories about superfluidity in ways no earthbound experiment can. Materials scientists analyze their crusts, crystalline structures 10 billion times stronger than steel, for insights into unbreakable alloys. Even cryptography researchers examine pulsar signals as potential natural random number generators. They're precise yet unpredictable glitches mimicking ideal cryptographic keys. But the most revolutionary applications may lie in space exploration. Neutron stars could become the universe's ultimate lighthouses for interstellar navigation. Their pulsar beams sweep through space with atomic clock regularity, creating a celestial GPS system far beyond Earth's orbit. NASA's NICER experiment aboard the International Space Station has already tested this concept, using X-ray pulsars to determine the station's position in space with kilometer accuracy, a precursor to navigation systems that could guide spacecraft between stars without relying on fragile Earth-based signals. The sheer energy density of neutron star material also tantalizes engineers. While harvesting it remains firmly in science fiction, theoretical studies suggest that just grams of the ultra-compressed matter in their cores could power civilizations if stabilized. Though the technical hurdles dwarf current capabilities, the physics principles behind such concepts drive innovations in energy storage and quantum materials today. Perhaps most remarkably, neutron star research is reshaping our approach to fundamental questions about reality itself. Their extreme environments probe the boundaries between quantum mechanics and general relativity, testing whether spacetime remains smooth or becomes granular at microscopic scales. Some theories even suggest their vibrations might reveal hidden dimensions, cosmic echoes bouncing through realms beyond our perception. What begins as the study of a dead star's trembles could end up rewriting our understanding of the universe's very fabric. Neutron stars might seem like distant curiosities, but their extreme physics could one day propel humanity across the cosmos. While landing on one remains firmly in the realm of science fiction, their gravity would shred any spacecraft long before arrival. Their very existence challenges engineers to rethink what's possible. Consider pulsar navigation, a concept being tested right now aboard the International Space Station. NASA's NICER experiment has successfully used the clockwork pulses from these spinning neutron stars to determine the station's position in space with astonishing precision, like a celestial GPS. This isn't just a backup system. It's a prototype for future interstellar missions, where Earth-based navigation signals would take years to reach a probe near another star. The regular flashes from pulsars could become lighthouse beacons for galactic exploration, their predictable rhythms cutting through the chaos of deep space. Then there's the tantalizing idea of harvesting energy from neutron stars. Picture a civilization advanced enough to tap into the magnetic fury of a magnetar. Its magnetic field, storing enough energy to power human civilization could theoretically be harnessed through technologies we can barely imagine, perhaps using quantum energy transfer or spacetime manipulation. While firmly speculative, such concepts push physicists to explore energy solutions at scales beyond conventional nuclear fusion. Even the theoretical neutron star mining proposals, though wildly impractical with current understanding, highlight how studying these objects expands our vision of what resources might exist in the universe. A single teaspoon of neutron star material, if stabilized, could revolutionize energy storage or materials science with its incredible density. The influence of neutron stars on future technology extends to propulsion as well. Their relativistic jets, which accelerate particles to nearly light speed, serve as natural particle accelerators demonstrating physics we struggle to replicate in labs. Scientists studying these jets are uncovering principles that could inspire next-generation spacecraft engines, perhaps some variation of a pulsar-powered plasma drive. Even the gravitational waves from colliding neutron stars provide insights into manipulating spacetime itself, a concept that fuels theoretical warp drive designs. Beyond hardware, neutron stars are reshaping how we approach problem solving. The same machine learning algorithms developed to sift through pulsar data now help detect gravitational waves and even diagnose medical conditions. Quantum sensors precise enough to measure neutron star vibrations could lead to communication networks or ultra-sensitive earthquake detectors. The interdisciplinary spillover from studying these cosmic extremes proves that curiosity-driven research often yields unexpected earthly benefits. Perhaps most importantly, neutron stars serve as cosmic classrooms. Their extreme conditions force us to question assumptions about matter, energy, and the laws of physics. Each vibration we decode, each flare we analyze, adds another piece to the puzzle of how the universe operates under stresses we can't recreate on Earth. They challenge us to think bigger, not just about how to reach the stars, but how to understand them. And as we'll see next, their influence extends far beyond technology, shaping the very building blocks of the cosmos itself. Neutron stars are the universe's ultimate alchemists, forging elements heavier than iron in cosmic crucibles of unimaginable violence. When two of these dense remnants spiral together in a fateful dance, their collision unleashes energies so intense they briefly outshine entire galaxies. In these fleeting moments, neutrons bombard atomic nuclei at breakneck speeds, rapidly building heavier elements through a process called rapid neutron capture. The aftermath scatters freshly minted gold, platinum, and uranium across interstellar space, precious stardust that will eventually seed new planetary systems. This cosmic recycling program explains why Earth's crust contains these rare metals. The jewelry we wear and the electronics we depend on all contain atoms born in neutron star cataclysms that occurred billions of years before our solar system formed. Beyond creating heavy elements, neutron stars sculpt their galactic neighborhoods through powerful winds and jets. A single pulsar's relativistic outflow, particles accelerated to nearly light speed, can carve cavities in interstellar clouds spanning light years. These cosmic bubbles act like stellar nurseries, compressing surrounding gas to trigger new star formation while simultaneously preventing nearby clouds from collapsing too soon. It's a delicate feedback loop where the death throes of massive stars govern the birth of their successors. Some neutron stars even act as cosmic ray accelerators, their intense magnetic fields launching atomic nuclei across the galaxy at energies surpassing human-made particle colliders. These high-speed particles contribute to the ionization of interstellar gas, subtly influencing the chemistry of future molecular clouds where planets might one day form. The vibrations we detect from these stellar remnants carry encoded messages about nature's fundamental forces. Each oscillation mode serves as a probe into extreme physics, testing whether general relativity holds under crushing gravity, revealing how nuclear forces behave at densities where atoms cease to exist. Some vibration patterns hint at quantum phenomena operating on macroscopic scales, where the star's entire core might behave as a single quantum fluid. Others suggest spacetime itself may become granular near the surface, like a cosmic version of pixels emerging at the smallest scales. These aren't just academic curiosities. Understanding how matter behaves under such extremes could revolutionize everything from energy production to materials science here on Earth. Perhaps most remarkably, neutron star mergers create the only environments hot and dense enough to temporarily recreate conditions from the universe's first microseconds. The vibrations following such collisions provide glimpses into how quarks and gluons, the building blocks of protons and neutrons, behave when freed from their normal confinement. These fleeting moments offer our best window into the primordial soup that filled the cosmos before atoms even existed. By studying these echoes of creation, we're not just learning about dead stars. We're piecing together the universe's origin story written in vibrations that ripple across space and time. In their death, massive stars give rise to objects that continue shaping the cosmos long after their fiery demise. The gold in a wedding ring, the uranium powering reactors, even the distribution of stars across galaxies, all bear the fingerprints of neutron stars' enduring influence. Their vibrations serve as both memorial and messenger, carrying secrets from the universe's most extreme environments to our waiting telescopes and detectors. Each pulse, each quake, each gravitational ripple adds another verse to an epic billions of years in the telling, a story where stellar death begets cosmic rebirth, and the faintest tremors reveal the deepest truths. Neutron stars do more than challenge physics. They reshape how we see our place in the cosmos. These ultradense remnants, vibrating with mathematical precision, whisper a profound truth. The universe operates on scales both unimaginably vast and infinitesimally small, yet everything remains deeply connected. When it reverberates through a neutron star's crust, it doesn't just send tremors through matter, it sends ripples through our understanding of reality itself. What we perceive as solid ground beneath our feet is, in cosmic terms, mostly empty space between atoms. But in a neutron star, even that illusion shatters. Here, matter is compressed so tightly that the very concept of solid dissolves into a quantum sea where particles lose their individuality, behaving more like waves in an ocean than discrete objects. This isn't just exotic astronomy, it's a mirror held up to the fluid nature of existence. Consider how these cosmic vibrations bridge distance and time. The gravitational waves from a neutron star collision billions of years ago still ripple through the universe today, subtly stretching and compressing spacetime as they pass. Every atom in your body has been shaped by such ancient events: the gold in a wedding ring, the iodine in your thyroid, even the calcium in your bones were forged in stellar explosions and scattered across the galaxy by neutron star mergers. These vibrations remind us that we're not just observers of the cosmos. We're literal stardust, woven from the remnants of dead stars and the echoes of their tremors. The study of neutron stars also blurs the line between the tangible and the theoretical. Their extreme conditions force us to confront questions that hover at the edge of philosophy. Can spacetime itself vibrate like a musical instrument? Is matter fundamentally solid or just energy trapped in temporary patterns? When a magnetar's magnetic field snaps and releases a burst of gamma rays, it's not just a celestial event. It's a challenge to our notions of cause and effect, playing out in realms where quantum uncertainty and relativistic gravity collide. Perhaps most humbling is how these silent giants expose the limits of human perception. A neutron star's vibrations occur at frequencies far beyond what our senses can detect, some too slow, unfolding over years, others too fast, pulsing in microseconds. Yet through ingenuity, we've built instruments to hear these cosmic rhythms, translating them into forms we can comprehend. In doing so, we've discovered that the universe speaks in harmonies our ancestors couldn't have imagined, a reminder that reality extends far beyond what our biology evolved to perceive. This journey through the silent symphony leaves us with indelible insights. Neutron stars teach us that matter under pressure doesn't just break, it transforms, revealing layers of complexity invisible under ordinary conditions. They show us how vibrations can carry information across unimaginable distances, encoding secrets in frequencies rather than words. And they prove that even in the darkest corners of the cosmos, there's music, if only we learn how to listen. From the quantum oddities in their cores to the gravitational waves they broadcast, these cosmic giants don't just obey the laws of physics, they help us write them. The silent symphony of neutron stars isn't just a cosmic curiosity, it's a revolution in how we understand reality itself. These celestial tuning forks vibrate with secrets about matter pushed beyond breaking point, gravity warping spacetime, and quantum physics playing out on stellar scales. Every tremor, every pulse, every glitch in their rhythm carries encoded messages from nature's most extreme laboratory, a place where the rules we take for granted on Earth shatter like glass under pressure. What makes these vibrations so extraordinary is their universality. The same physics that causes a neutron star's crust to quake after a magnetic upheaval also governs how particles interact in our most advanced colliders. The superfluid vortices swirling beneath their surfaces mirror quantum phenomena we're only beginning to harness in technologies like superconductors. Even the gravitational waves they emit aren't just space-time ripples. They're proof that the universe communicates through vibrations across every scale, from the subatomic to the galactic. This symphony matters because it reminds us how much we still have to learn. For centuries, humans believed we'd uncovered nature's fundamental laws, only for discoveries like neutron stars to reveal entire new layers of complexity. The very existence of magnetars, with magnetic fields so strong they distort atoms from thousands of miles away, challenges our assumptions about how matter and energy interact. Their vibrations expose gaps in our knowledge that could lead to breakthroughs we can't yet imagine, much like how studying stars a century ago unexpectedly gave us nuclear energy and quantum mechanics. Beyond pure science, neutron stars embody humanity's relentless curiosity. They represent questions we didn't even know to ask until technology caught up with cosmic reality, like how a civilization without radio telescopes could never have conceived of pulsars. Today, as we translate their vibrations into sound waves and visualizations, we're not just analyzing data, we're learning to perceive dimensions of reality our senses evolved too early to detect. The silent symphony ultimately sings of connection. The gold in your jewelry, the uranium powering cities, even the calcium in your bones were forged in neutron star collisions billions of years ago. Their vibrations link us to the universe's most violent and creative processes, proving that even in the void of space, nothing truly exists in isolation. As we continue listening with ever more sensitive telescopes, gravitational wave detectors, and quantum sensors, we're not just studying distant stars. We're decoding the universe's hidden language, one vibration at a time. The silent symphony of neutron stars is more than just a cosmic spectacle. It's a living laboratory where the universe tests its most extreme physics. Every vibration, every quake, every pulse from these stellar remnants carries encrypted messages about how matter behaves when pushed beyond any earthly limit. But this isn't just about unraveling stellar mysteries. It's about rewriting the textbooks of physics itself. The oscillations rippling through a neutron star's crust today might hold clues to questions that have puzzled scientists for generations. What lies at the boundary between quantum mechanics and gravity? Does spacetime remain smooth or become grainy at microscopic scales? These aren't abstract thought experiments anymore. They're tangible puzzles waiting to be solved in the vibrations of distant, spinning stellar corpses. Consider how far we've come in just a few decades. The first pulsar discovered in 1967 was initially mistaken for an alien beacon. Its regular pulses seemed too perfect to be natural. Today, we recognize these cosmic lighthouses as neutron stars spinning with metronomic precision, their beams sweeping across the galaxy like celestial searchlights. But the real breakthrough came when we realized these pulses weren't just signals. They were vibrations, subtle tremors that could reveal the star's hidden interior structure. It's as if the universe handed us a stethoscope to listen to stellar heartbeats across interstellar space. The implications stretch far beyond astrophysics. The same quantum phenomena that make neutron stars vibrate, superfluidity, superconductivity, quark confinement, are principles we're struggling to harness here on Earth. When physicists study how vibrations travel through a neutron star's superfluid core, they're glimpsing behaviors that could revolutionize energy transmission or materials science. The crust of a neutron star, with its crystalline structure 10 billion times stronger than steel, inspires theories about unbreakable materials. Even the star's magnetic fields, capable of storing energies surpassing all human power consumption, hint at possibilities we're only beginning to imagine. This cosmic connection touches our daily lives in surprising ways. The gold in your jewelry, the uranium in nuclear reactors, even the iodine in your thyroid. These heavy elements were forged in neutron star collisions billions of years before our solar system formed. The vibrations we detect from distant stellar remnants today carry echoes of those ancient cataclysms, linking us to events that shaped the very atoms we're made of. It's a humbling thought. The same forces that make a neutron star quake after a crust fracture also determine the elemental ingredients that make life possible. As technology advances, our ability to listen to this silent symphony grows ever more sophisticated. Gravitational wave detectors now sense spacetime ripples from colliding neutron stars across cosmic distances. X-ray telescopes map surface vibrations with millimeter precision, while quantum sensors promise to detect oscillations too subtle for current instruments. With each leap forward, we're not just building better tools, we're expanding our capacity to hear the universe's hidden music. The next time you look up at the night sky, remember this. Scattered across the darkness are countless cosmic tuning forks, each vibrating with secrets about matter, energy, and the fabric of reality itself. Their song is silent, carried not through air but through the curvature of spacetime, yet it speaks volumes about how the universe works at its most fundamental level. If these celestial giants have taught us anything, it's that nature's most profound truths often reveal themselves not in grand pronouncements, but in subtle vibrations waiting for those patient enough to listen. If this journey through the cosmos has sparked your curiosity, consider joining our community of space enthusiasts. Hit that like button, subscribe for more deep dives into the universe's wonders, and share your thoughts in the comments below. What cosmic mystery should we explore next? Until then, keep looking up and remember, the universe is always humming its silent symphony. We just need to learn how to